Up till now, we analyzed the transmission line characteristics using analytical approach. There is another approach which is a very elegant approach, and that is the graphical approach for analyzing the problems of transmission line. In fact, the graphical approach has many advantages. Firstly, we all know that an image has much longer lasting impression than an equation or a text. So, if the characteristics of transmission line are represented in the form of an image, it creates a much longer lasting impression on the human mind. Secondly, we will see later that the graphical approach is much simpler compared to the analytical approach, where the calculations can be reduced by a significant amount when we analyze the problems on transmission line. Thirdly, and most importantly, the graphical approach is a very compact way of representing the impedance characteristics of transmission line. So, in fact, whenever we are doing transmission line calculations, even analytically, it will be appropriate to keep the graphical representation in mind, and any analytical result which we get on transmission line should always be cross checked with the graphical representation. So, one does not go at least conceptually wrong in solving the transmission line problems. The graphical approach for solving transmission line problem essentially is for solving the impedance characteristics of transmission line. This approach does not give you the voltage and current solutions. It gives you only the representation of impedances on transmission lines or the standing wave characteristics of transmission line. That means, it can give you the impedance transformation relationship, it can give you calculation of the reflection coefficients, the calculation of VSWR, the location of the voltage minima, the location of voltage maxima, right, and so on and so on. So, today we develop a basic framework for analyzing the transmission lines by graphical approach. The basic idea here is to take the impedance which is normalized to the characteristic impedance and do transformation of this impedance into the complex reflection coefficient plane, what is called the gamma plane. By doing this, then we transform all the impedances from the impedance plane to the reflection coefficient plane, and then we will see that this representation of impedances in reflection coefficient plane makes the calculation much simpler than if we carried out the calculation in the impedance plane. As we all know that the impedances, if we take the passive impedances, their resistive part is real and positive, and the imaginary part could be positive or negative. That means, we are saying that the resistance in any impedance is always positive. We are not talking about negative resistances here, and the reactance could be positive, that means it could represent inductance, or it could be capacitive, so it will be negative. So, if I plot a impedance point on the complex impedance plane, I get the impedance plane where the real axis represents the resistance and the imaginary axis represents the reactance. Before we get into this plotting, first let us understand that the impedances in transmission line calculations always are the normalized impedances with respect to the characteristic impedance. As we saw earlier, the absolute impedances do not have much meaning in transmission line calculations. The impedances always have to be normalized with respect to the characteristic impedance. In our framework now, let us first make an assumption that the transmission line is a lossless transmission line. That means, the characteristic impedance of this line is a real quantity, and all impedances which we have are now normalized with respect to the characteristic impedance Z0. So, any impedance Z normalized is nothing but the actual impedance divided by the characteristic impedance Z0. Let me write explicitly the real and imaginary part of the normalized impedance, and let me denote these by small alphabets. So, the normalized impedance is represented by R plus Jx, where R represents the resistive part of the normalized impedance and X represents the imaginary part of the normalized impedance. Then in the complex Z plane, this is now the complex Z plane or the normalized Z plane. I can put any point in this plane whose this value is R. So, the real axis is normalized resistance R and the imaginary axis is J times X. This value is X, Jx. So, this point here P represents an impedance which is having a normalized resistive value R and a normalized reactance value X. So, if I consider all possible passive loads for which the resistive part is always positive, then any point in the right half plane of this complex Z plane represent all possible loads. Also, the point which lie on the imaginary axis for which R is equal to 0, they represent the purely reactive loads. So, that means if I consider all points on the imaginary axis and the point which are lying on right half of the imaginary axis, they cover all possible passive loads which one can realize on transmission line. So, essentially the entire impedance plane which is right half of this represents the passive loads. Now, we know for every passive load we have a corresponding reflection coefficient value. So, as we have seen earlier, the reflection coefficient gamma that is equal to Z minus Z0 divided by Z plus Z0. For a lossless line, Z0 is a real quantity, Z in general could be complex. If I write this expression in the normalized impedances, I can take Z0 common from numerator and denominator. So, this will be Z normalized minus 1 divided by Z normalized plus 1. Writing explicitly for real and imaginary parts, the reflection coefficient can be written as R plus Jx minus 1 divided by R plus Jx plus 1. So, in general the reflection coefficient will have a real value and it will have an imaginary value. This can either be written in the Cartesian form or it can be written in the polar form. So, let us say the real part of the reflection coefficient is denoted by U and the imaginary part is denoted by V. So, the reflection coefficient can be written as U plus J V. If I represent the reflection coefficient into the polar form, this is also equal to the magnitude of the reflection coefficient R and some angle theta. So, the reflection coefficient gamma can be represented by a Cartesian number which is U plus JV, or it can be represented like a polar number which is having a magnitude R and an angle theta. Using this expression now, we have one-to-one correspondence between the reflection coefficient and the normalized impedance. So, if you know normalized impedance, we can find out the reflection coefficient. I can invert this relationship and get the normalized impedance Z, that is equal to 1 plus gamma divided by 1 minus gamma. So, if I know the value of normalized impedance, I can get uniquely the value of reflection coefficient, and if I know the value of reflection coefficient, complex reflection coefficient, then I can uniquely find the value of the corresponding impedance. So, this transformation between the reflection coefficient and the normalized impedance is a one-to-one transformation. Now, if I plot the reflection coefficients for all passive loads, as we have seen earlier, for passive loads the magnitude of the reflection coefficient is always less than or equal to 1. We saw when the impedance is purely reactive or short circuit or open circuit, that is the time the magnitude of the reflection coefficient becomes equal to 1. Otherwise, for any other impedance, the magnitude of reflection coefficient is always less than 1. That means, if I plot the reflection coefficient into the complex reflection coefficient plane, what we can call as the complex gamma plane. So, this is now my complex gamma plane, where the real axis is u, the imaginary axis is jv, and here we are marking the complex reflection coefficient. So, this is complex gamma plane. Since for all passive loads the magnitude of the reflection coefficient will be less than or equal to 1, all impedance points have a corresponding point of reflection coefficient which lies within the unity circle in the complex gamma plane. So, if I draw a unity circle whose radius is equal to 1, all passive loads reflection coefficient will lie within this circle. So, any point if I take within this circle, then that will have a corresponding passive load value, or if I take any passive load value, it will have a corresponding reflection coefficient point inside this circle, the unit circle. So, this is its radius is equal to 1. So, a reflection coefficient point here has a magnitude as we mentioned. So, if I represent that in the polar form, this distance from the center of the complex gamma plane gives you the magnitude of the reflection coefficient, and the angle of this vector from the real u axis, that gives you the angle theta. So, this point is the complex reflection coefficient point denoted by r e to the power j theta. It is having equivalent value of u and v. So, the complex reflection coefficient point can be marked on the gamma plane. So, now we have two planes. You are having a complex z plane and you are having a complex gamma plane. And as we know, since there is a one-to-one transformation between these two planes, every point on this plane essentially is mapped to a point on this plane. So, first exercise we do is we try to map all possible impedances onto the gamma plane, and then we essentially create a graphical structure where the analysis now carried out in the complex reflection coefficient plane. So, for doing this transformation, let me go back again to the original relation which I had, and that is the impedance I can write as normalized impedance z bar is equal to r plus jx, that is equal to 1 plus gamma divided by 1 minus gamma. Substituting for gamma is equal to u plus jv, I get r plus jx, that is equal to 1 plus u plus jv divided by 1 minus u plus jv. I can rationalize this function and separate out the real and imaginary parts. So, I will get r equal to some function of u and v, similarly x equal to some function of u and v. So, from this relation I will get two equations on the complex gamma plane for a given value of r or x. So, essentially when I map the impedances on the complex gamma plane, I will see two set of curves on the complex gamma plane. One will correspond to a given value of r, other will correspond to a given value of x. So, if I separate out the real and imaginary parts, essentially I will get the two equations, and these equations will be given by this. So, this is the equation corresponding to the real part of this equation. So, if I take r equal to real part of that and rearrange, I will get an equation which will be this. Similarly, if I take x equal to imaginary part of this and rearrange the terms, I will get an equation which will look like that. Now, if I look at this equation, immediately it strikes to us that both the equation represent circles on the complex gamma plane. So, for any given value of r, I get a circle on the complex gamma plane. Similarly, for any value of x, I get a circle on the complex gamma plane. What then this represents is that for a given value of r, if I take different values of the reactances or x, then I am going to move on this circle. It is a locus of all reactance points for a given value of r. That is the reason we call these circles as the constant resistance circles. So, these circles represent different values of reactances, but all the points which are lying on this circle, they have the same resistance value. Similarly, when I go to this circle, it is a locus of the points of different resistances, and all of them have the same reactance value. So, these circles are what are called the constant reactance circle. Once we realize that, then one would like to see graphically how this circle would look like on the complex gamma plane. So, to draw the circles, we can get the center and the radius of the circles. So, for a constant resistance circle, the center is r divided by r plus 1 comma 0. That means the centers of all these circles, constant resistance circle, they lie on the real gamma axis, they lie on the u axis, and the radius of this circle is equal to 1 upon r plus 1, where r will vary from 0 to infinity. Similarly, when I go to the constant reactance circle, I have a center which lies at 1 comma 1 upon x. That means this center lies on a vertical line passing through u equal to 1, and its radius of these circles will be given by 1 upon x. So, first we graphically draw these two sets of circles and see how they look like. So, let us take first the constant resistance circle. So, this is our complex gamma plane, u j v. So, I am drawing now the complex gamma plane, and what we are drawing is the constant r circles or the constant resistance circles. So, as we saw, the center for this circle is r upon r plus 1. So, let me write again. So, the center is r upon r plus 1 comma 0, and the radius for this circle is equal to 1 upon r plus 1. So, the constant resistance circles have a center which is r upon r plus 1 comma 0, and its radius is 1 upon r plus 1. Let us now try to plot this circle for different values of r. So, let us vary the value of r from 0 to infinity, and then see how these circles will get plotted on this complex gamma plane. So, if I take r equal to 0, the center, this quantity becomes 0. So, I get a center which is 0 0, which is the origin of the complex gamma plane, and for r equal to 0, the radius of the circle is equal to 1. So, the unity circle in the complex gamma plane itself represents a constant resistance circle corresponding to r equal to 0. So, this circle corresponds to r equal to 0. Let us take another value of r, and the special value of r will be r equal to 1, which will correspond to z equal to z0. So, if I put r equal to 1 in this is 1, r plus 1, that will be equal to 2. So, this will be 1 upon 2 comma 0. So, the center of this circle will lie halfway between these 2 points, because this is 0 origin and this is unity circle, that is equal to 1. So, the center for r equal to 1 circle lies halfway here, and the radius is equal to half. So, this circle is having a radius which is equal to this and the center here. So, this circle passes through origin and will look like that. If I increase the value of r further, one thing we will note is that the center shifts towards the right and the radius of the circle becomes smaller and smaller. If I take the extreme value, that is r equal to infinity, then this center, this will become 1. So, this will be 1 comma 0 and the radius will become equal to 0. So, for r equal to infinity, the circle will degenerate into a point at this location. So, if I take different values of r, this circle essentially lie one within another like that with increasing value of r, and at this point, this location here, that represents r equal to infinity. In fact, one can see from this equation for the constant resistance circle that all these curves here, they pass through the point u equal to 1, v equal to 0. So, all this circle which you have drawn here, they pass through this point u equal to 1, v equal to 0. Similarly, even these circles which are constant reactance circle, they also pass through the same point u equal to 1, v equal to 0. So, this point is rather a special point, because both the set of curves, whether you take constant resistance circles or constant reactance circle, they pass through this special point. So, u equal to 1, v equal to 0, that is the location from which the circles essentially are going to pass. So, if I show you this circle, which are the constant resistance circle, this circle essentially look like that. So, just to give you few numbers here, this circle, which is the outermost circle, that corresponds to r equal to 0. This circle which passes through the origin, that is r equal to 1. Then as you go for higher and higher value of r, this is r equal to 2 circle, 5 circle, 10 circle, and the final point here u equal to 1, v equal to 0 point, that corresponds to r equal to infinity. So, the constant resistance circle are one within another, and the r equal to 0 gives you the largest circle, and as the r increases, the circle becomes smaller and smaller, and the final for r equal to infinity, the circle becomes a point. So, this is the one set of curves which you will get, which will correspond to the constant resistance of the impedance. The another set of circles which are the constant reactance circles. So, here let us now draw the constant reactance circle. This is u, this is JV, again this is complex gamma plane, and these are the constant X circles or constant reactance circles. The center for these circles, as we saw, is 1 comma 1 upon x, and radius for this circle is equal to 1 upon x. Again, let us substitute different values of x and plot this circle on the complex gamma plane. This is origin, which is u equal to 0, v equal to 0. If I put x equal to 0, then the center of this circle is 1 comma infinity, and the radius of this circle is also infinity. Now, the radius of the circle equal to infinity means this circle has become a straight line. But we know this circle, as I mentioned earlier, passed through this point u equal to 1, v equal to 0. That means I now have a circle which passes through u equal to 1, v equal to 0 point, and it is a straight line. Okay. So, the real axis of the complex gamma plane corresponds to x equal to 0. So, all the reactance values 0 correspond to this line. So, this line itself corresponds to x equal to 0. Now, consider there are two types of reactances, the positive reactance, which is inductive, or the negative reactance, which is capacitive. Let us say first I take the inductive reactances, that means x is positive. So, as x becomes larger, the center which lies on 1 comma 1 plus x, that means it always lies on a line which is u is equal to 1. So, as I increase the value of x, the center which was at infinity, that now comes down, and the radius also becomes smaller and smaller. So, I get, initially I had a circle which was this straight line. Now, as I increase the value of x, I will get a circle which will have a smaller radius, and so on and so on. Take the extreme value when x is equal to infinity. At that point, this quantity will be 0. So, the center will become 1 comma 0, which is this point, and the radius of this circle will become equal to 0. So, this point again represents x equal to infinity. So, it is interesting that this circle which was r equal to infinity, that also corresponded to this point also represents x equal to infinity. So, if I plot now the various circles, now again first thing we should note here that we are only interested in reflection coefficients which lie within the unit circle, because they correspond to the passive loads. If any portion of these circles, the constant reactance circles, which lie outside the unity circle, is not of our relevance, because that portion of the curve does not represent a passive load. So, although the constant reactance circle fill the entire space, only that portion of the constant reactance circle is useful to us which lies within the unity circle of the complex gamma plane. So, if I draw now these circles will essentially look like that. These are the constant reactance circles, they become smaller and smaller like this. So, only this portion of the curve is meaningful to us, like that. So, all positive value of x, that the inductive reactances, their center will always lie on this line, but on the upper half of the complex gamma plane, and that is the reason this circle will be always lying above the u axis. So, these curves which are within the unity circle, they represent the reactive parts corresponding to the passive loads. Similarly, I can take negative values of x, I will get mirror image of these circles on the lower half. So, I will get the set of curves which will look like that, and again we take only those portions of the curve which lie within the unit circle, because they are the one which will correspond to the passive loads. So, if I take different values of x and plot this, the curve essentially will look like that. So, this horizontal line here, that corresponds to x equal to 0, except the point which is this extreme point here on the unit circle, because that point corresponds to x equal to infinity. These circles are for higher values of x. The upper half of this represent the positive value of x, and the lower half of this represents the negative value of x. That means, if I am talking about reactances, then upper half of these circles represents the inductive reactances, and the lower half represents the capacitive reactances. So, now I have got two sets of circles, the constant resistance circle within the unity circle of the complex gamma plane. I have got the constant reactance circles again plotted within the unity circles of the complex gamma plane. If I want to identify now a impedance point, I can superimpose these two set of circles, and essentially I have created a coordinate system for plotting a impedance point on the gamma plane. That is what essentially we do. We take these two sets of circles and superimpose within the unity circle of the complex gamma plane. Just for the clarity, we have drawn here only very few circles. One is this outermost circle, which is the unity circle. This is the u axis, that is the v axis, and then this circle corresponds to r equal to 1. These circles corresponds to x equal to 1, and the horizontal line here, as we saw, that corresponds to x equal to 0. This point here is x equal to infinity. This point also represents r equal to infinity. So, let us now see the gross characteristic of these two sets of circles. Firstly, all constant resistance circles have their centers lying on the positive real axis of the complex gamma plane. All the circle pass through the point u equal to 1, v equal to 0. As the value of r increases, the center shifts towards right from the origin to u equal to 1, and the radius decreases. So, this point here corresponds to r equal to 0, or this circle corresponds to r equal to 0, and this point corresponds to r equal to infinity. Similarly, to summarize the characteristics of constant reactance circle, the constant reactance circle lie on the vertical line passing through u equal to 1, and the upper half of the circles represent the positive reactances, and the lower half represent the negative reactances. As the reactance value increases, the center of the circle approaches towards u axis, and the radius of the circle goes on reducing. So, the size of the circle reduces, and ultimately when x is equal to infinity, the size of the circle becomes equal to 0. So, this point again represent x equal to infinity. Now, the superposition of these two circles, as I mentioned, is now the coordinate system for impedance on the complex gamma plane. That is what is called the Smith chart, and Smith chart is a very powerful tool for analyzing the transmission line problems. Essentially, now we have created a tool, graphical tool, where impedances are represented on the complex gamma plane, and now without going back to the impedance plane, I can now from these two sets of circles, I can directly mark the impedances on the complex gamma plane or on the Smith chart. Normally, these Smith charts are readily available for calculations. So, one does not have to draw the Smith chart, having understood that the Smith chart is a superposition of constant resistance and constant reactance circles. We get a figure something like this. This is what is called a Smith chart. So, as we can see here in this circle, this is the unity circle, this is the real axis of gamma, which is u axis, the center here, that is the origin of the complex gamma plane. These circles, which are flaring like that, they are the constant reactance circles, and these circles which are one within another, they represent the constant resistance circles. So, now if I want to plot or mark a point on impedance on the complex gamma plane, I can, these are coordinate system which I am having now, and this is the orthogonal coordinate system. So, you can take the corresponding value of r and x and find the intersection of these two circles corresponding to that constant value r and the constant value x, and the intersection point will represent an impedance for that value of r and x. So, now every time without going into the transformation, I can read from this itself the value of r and x and directly mark a impedance point on the complex gamma plane. So, this is a extremely powerful tool, what is called a Smith chart, and now we will see this Smith chart can be used for doing various types of transmission line calculations. However, before we go into this analysis of the transmission line, let us first identify some special points on the Smith chart. So, let me take a simplified version of the Smith chart, only very few circles drawn for the clarity. So, the Smith chart will look something like that, and let me mark some very specific points as a landmark points on the Smith chart. Let us say we are now considering the impedances which are given by R plus Jx. So, R is the resistance and X is the reactance. This point here A, as we have seen, any point lying on the outermost circle represent R equal to 0. Any point lying on this horizontal axis represents x equal to 0. So, the intersection of these two, the horizontal axis and the unit circle, which is the point A, that corresponds to r equal to 0, x equal to 0. So, this point we have r equal to 0, you have x equal to 0. And from impedance point of view, when r is equal to 0, x is equal to 0, this load is nothing but the short circuit. So, on the Smith chart, this point A represents a short circuit point. So, this load, this thing is what is called the short circuit point. Similarly, if I go to the other point here B, this point, as we saw, the two sets of circles degenerate into a point, and that is this point. So, this point corresponds to r equal to infinity. It also corresponds to x equal to infinity. So, this point here is r equal to infinity, it is also x equal to infinity. So, that means the impedance is infinity. So, this point is nothing but the open circuit point. So, you have this circle which is the open circuit point. So, the leftmost point on the Smith chart corresponds to the short circuit load, the rightmost point on the Smith chart corresponds to the open circuit load. All the points which are lying on the outermost circle represent pure reactances. So, any point on the outermost circle is pure reactance, because for these points r is equal to 0. So, you have points which are lying on the outermost circle for which the x value changes, but r is always equal to 0. So, they essentially represent the pure reactances. As we saw, the upper half of this circle corresponds to the positive value of x, and positive value of x means inductive reactances. So, the unity circle which is in the upper half, that corresponds to the purely inductive reactances or purely inductive loads. Similarly, the point which are lying on this circle on the lower half, they represent purely capacitive loads. If I go now inside this circle, I will have some value of r here, but in the upper half of this circle the x value will be always positive. That means all the point in the upper half of this circle represent the inductive loads, and the point which are on the lower half of this circle, they represent the capacitive loads. So, just looking at the point, once the point is marked on the Smith chart, visually I can immediately tell whether the load is capacitive load or the load is the inductive load. We can take again a special point here, this circle which passes through the uppermost point of the Smith chart, that has a value x is equal to 1. So, this point here, C point, that corresponds to r equal to 0, because it is lying on the outermost circle for which r is equal to 0, and its x value is equal to 1. So, this point corresponds to r equal to 0, x is equal to plus 1. So, this point represents a pure reactance whose magnitude is equal to the characteristic impedance of the line. Similarly, the lowermost point D corresponds to r equal to 0 and x equal to minus 1. So, this point represents a purely capacitive reactance whose magnitude is equal to the characteristic impedance of the line. There is one more special point, and that is the center of the Smith chart. This point, the point M, which is the origin of the Smith chart or the origin of the complex gamma plane, is the intersection of the r equal to 1 circle and x equal to 0 line. So, this point here represents r equal to 1 and x equal to 0. So, this is r equal to 1, x equal to 0. That means at this location the impedance is equal to the characteristic impedance of the line, and that is the point which is of greatest interest to us, because that point represents the match condition on the transmission line. So, when the impedance lies on the center of the Smith chart, which corresponds to the magnitude of the reflection coefficient 0, this point represents the match condition on the transmission line. So, now once we understand the various specific points on the Smith chart, then now we can go back and now mark the reflection coefficient on this Smith chart. So, the Smith chart now has given you the coordinate system, which is in terms of r and x, which is a very complicated coordinate system, but the complex reflection coefficient axis is not drawn on the Smith chart. It is understood that whenever we are having a Smith chart, the horizontal line passing through the center of the Smith chart, that is the real gamma axis, whereas the vertical line is the imaginary gamma axis. Also, it should be kept in mind that the Smith chart, if I look at the Smith chart properly, since it is a complex gamma plane, it should be always held like this. The most clustered portion of the circle should be on the right hand of the user, because the real axis of complex gamma plane is in this direction, and the positive imaginary axis of complex gamma plane is in vertical direction. So, we should not use the Smith chart like that, or we should not use the Smith chart like this. We should keep the Smith chart like this, so that the complex reflection coefficient axis is properly defined. So, normally on the Smith chart the reflection coefficient axis is not drawn, but the user must remember that the Smith chart is nothing but the set of constant resistance and constant reactance circle drawn on the complex gamma plane. Once I get that, then I can now do simple calculations of conversion from the reflection coefficient to the impedances or vice versa in a very simple manner. I can just mark a point of impedance on the Smith chart and then treat this thing as a complex gamma plane and find out the coordinates of that point in the complex gamma plane, which will give me the complex reflection coefficient. So, the conversion of impedances to the complex reflection coefficient and vice versa has become extremely simple when the Smith chart is available to the user. So, for analyzing the transmission line problem, the Smith chart is a very handy tool, and we will see later that many complex impedance transformation problems can be solved by using the Smith chart. Before we get into that, however, let us try to look at not only the impedances but the admittances. Up till now we have done the analysis assuming that the impedances are represented by the only resistance and reactive part. Many times when the transmission lines or impedances are connected in parallel, it turns out to be more handy to do the calculation in terms of admittances rather than in terms of impedances. So, it will be worthwhile to first see how the Smith chart gets modified in terms of admittances, and then how do we do conversion from the impedances to the admittances and vice versa. So, let us quickly look at that instead of impedances I had admittances for the calculation. How would the transformation between the reflection coefficient and the admittance would go? Before we get into that, however, we have to define now the characteristic of transmission line in terms of admittances. So, to start with, we have to define the characteristic admittance of a transmission line, then we have to take any arbitrary admittance, then define the normalized admittance with respect to the characteristic admittance of a transmission line, and then we can find out the graphical representation of the transmission line in terms of the normalized admittances. So, next time when we meet, we first take the normalized admittances, find out the reflection coefficient in terms of normalized admittances, establish relationship between the real and imaginary part of the admittances, and then get the Smith chart and try to find out the relationship between the admittance Smith chart and the impedance Smith chart.